Humans have a natural instinct to take chaotic information and force it into sequential order. We line things up to make sense of them. In computer science, this instinct is formalized into something called a list abstract data type, or ADT. An ADT is essentially a contract. It guarantees that you can take a sequence of data and perform specific actions on it. You can create a list, insert a new item, search for an existing one, delete an item, or display the whole sequence. But the key word here is abstract. This contract is a theoretical black box. It dictates exactly what operations are allowed, while entirely ignoring the physical reality of how the computer actually stores those numbers. On a whiteboard, adding a new student to a class roster appears instantaneous. You draw a new box, write a name, and you're done. Inside a computer, that exact same action requires physical, electrical work. Programming is the act of dragging these theoretical concepts down into the physical constraints of hardware. And the moment you do that, you are forced to make immediate engineering trade-offs. To understand the gravity of those engineering trade-offs, we first have to look at the physical environment where the data actually lives. Physical system memory, your computer's RAM, operates like a massive, rigid grid of empty microscopic boxes. Every single piece of data you save must claim a specific physical coordinate on this grid. This creates an immediate engineering tension. A list, by its very nature, is dynamic. It grows, shrinks, and rearranges itself. But the silicon grid holding it is totally inflexible. To solve this problem, computer science offers two entirely divergent architectural solutions. Each approach uses the hardware differently, and each comes with severe consequences for system performance. You have to choose between an array and a linked list. And that single choice will dictate the speed, efficiency, and capability of your entire software system. This diagram shows an array. It is an architecture that allocates a fixed, continuous block of memory. The data is stored back to back, locked strictly into adjacent physical slots. By forcing the data to sit directly next to each other, you gain one massive advantage: instantaneous access. Because the hardware knows the exact memory address where the list begins, and it knows the blocks are contiguous, it can mathematically calculate the physical location of any item and jump straight to it. In algorithmic terms, this is O1 time complexity. The speed is absolute, regardless of whether the array holds 10 items or 10 million. But this rigid structure has a fatal flaw. Watch what happens when we try an insert operation, dropping the number 50 into the middle of the existing sequence. Because the physical space is strictly consecutive, two items cannot share the same slot. To make room for the new number, the system has to initiate a physical cascade. This is the shift penalty. To insert a single piece of data, the processor must copy every element to the right of the target and physically move it one space down the line. If the shifting penalty is crippling your software, the only solution is to abandon contiguous memory entirely. This brings us to the linked list. Instead of forcing data into a neat row, a linked list allows data to scatter randomly across the empty pockets of the memory grid, connected only by directional pointers. We achieve this by building a custom structure called a node. A node stores two things: the actual data you care about and a memory address, a literal compass pointing the processor to the exact location of the next item in the sequence. When we rerun our insertion operation, the advantage becomes obvious. The computer finds any random empty spot for the number 50. Then it simply snips the pointer coming from 10, rewires it to 50, and points 50 to 20. Not a single piece of existing data had to move. Bypassing the shift penalty makes insertion and deletion an instant O of 1 operation. But flexibility has a price. Because you abandoned contiguous alignment, the computer can no longer calculate where a specific item is located. To find the 100th item, you must start at the very beginning and follow 99 separate pointers to get there. Your search time plummets to O of n. You are trading read speed and spending extra RAM on pointer addresses, specifically to achieve flawless, dynamic modification. For highly volatile datasets, it is a mandatory trade. Let's look at how this trade-off dictates performance in a high-stakes scenario, like processing a digital image, a network graph, or a scientific simulation. This diagram illustrates a sparse matrix. It's a dataset where the vast majority of the information is empty, consisting entirely of zeros. If you force this sparse data into a rigid array, the computer must allocate physical RAM for every single cell. You end up wasting huge amounts of memory storing thousands of useless zeros, simply to maintain the structural shape of the grid. To stop the memory bleed, we extract the data using a 3-tuple representation. The empty space is discarded completely. By storing only the exact row coordinate, column coordinate, and the specific value of the non-zero elements, we collapse massive, mostly empty grids into tiny, highly efficient dynamic lists. When your data includes vast voids of nothingness, rigid arrays become computational liabilities. Dynamic extraction is the only way to process without exhausting the hardware. This principle extends directly into complex mathematics, particularly algebraic polynomial equations. Take an equation like 4x to the power of 100 plus 3x squared. If you model that as an array based on exponents, you run into the exact same sparsity problem. The system will force you to store 97 consecutive zeros to account for all the missing terms between the 100th power and the second power. By modeling it as a linked list, the sparsity vanishes. Each node strictly stores the coefficient and the power and points directly to the next valid term. Adding two complex polynomials together then becomes a simple exercise of traversing two linked lists simultaneously, summing the coefficients whenever the exponents match. Linked lists allow software to model high-level mathematics dynamically, skipping over empty computational space entirely and processing only the actual values. The ultimate proof of pointer flexibility is how it handles continuous elimination. It's best demonstrated by a classic algorithm called the Josephus problem. The rules of the simulation are simple. N people stand in a circle. Counting begins at the first position, and every kth person is eliminated until only one survivor remains. If you try to run this simulation using an array, the system chokes. Every elimination triggers a massive shifting cascade, and the array struggles mathematically to smoothly wrap the counting from the end of the line back to the beginning. But a circular linked list models the physical reality of a circle perfectly. We take the next pointer of the final node and aim it back at the head node. Now, the elimination phase is incredibly lightweight. The system traverses k steps, grabs the pointer before the target, and bypasses it. The target drops out instantly. No massive data shifts, no out-of-bounds errors. Bending the memory architecture directly dictates what algorithms are realistically possible for the machine to execute. This dashboard highlights the final engineering compromise. Arrays win easily when you need to read static, densely packed data. Linked lists win the moment that data becomes sparse or requires constant modification. Just remember that the linked list's dynamic flexibility is heavily taxed by the physical reality of the hardware. You are sacrificing memory to store thousands of directional pointers. In computer science, there is no universally perfect data structure. There is only a series of precise compromises. True algorithmic design is the ability to correctly match the mathematical shape of your data to the physical limitations of your hardware.